I'm super excited to share the current work that I'm working on and hopefully gain some insight from all of y'all, whether you're early or later in your careers, about advice and other things that I can explore within my thesis. So I want to give a quick introduction into who I am. My name is Mikayla. I use she, her pronouns. And I like to call home LA. That's where I was born and raised. Middlebury, where I went to undergrad, and now Austin, where I currently live. And so these are just a group of pictures of what I identify with and what has helped me pursue higher education. I am a POSSE Scholar, which is a 4-year full tuition leadership program. And I was able to attend Middlebury with my tuition paid and join 9 other students. And so I appreciate that program for letting me be where I am today. In addition, I'm a Banatao Scholar. The Banatao family invests in Filipinos in science and engineering. And so a lot of that has affiliated with my time as an undergrad, whether that's exploring science or helping other Filipinos to pursue higher education in science and engineering. And not here today, but I'm sure all of you have seen around, is my dog Saki. This is my family right here. I have 2 brothers and my parents are there. And so, yeah, these are some of the things that I hold near and dear to me and my identity. And so I want to go into my background as to why I call myself a glaciologist. So I intended on going to Middlebury to research chemistry and research cancer, but during one of my first labs there as like a POSSE Scholar, we were able to kind of tour all of the science departments there, and our geology department at the time had a research vessel. And so being out on Lake Champlain, which is the 5th largest lake in the United States, if you didn't know, and it borders in between upstate New York and Vermont, and it was like one of the most beautiful places that I've ever seen, and it really connected me to like the oceans and the lakes and the rivers that I grew up going to back home. And so I'm really lucky to have studied geology at a place like Middlebury, where it was a small department. Best friends that I have till today. This is Geophysics here in the middle during one of our structural geology labs. And yeah, and so you're probably wondering, okay, how do you become a geologist to a glaciologist? And that is due to, and I have to give them all of my praise and thanks to Liz Olty, who's now a faculty member at Middlebury College. And she pushed me, or encouraged me really, to apply for this REU program at Georgia Tech. There, I was advised by Alex Roble and John Christian. They are glaciologists and modelers within our community. And there I just learned the beauty of ice sheets and how I can explore these systems through models, simple models to complex models. But yeah, I started off with this group, and a lot of that work turned over into my senior thesis, where I incorporated the sediment model, which I'll be talking through with y'all throughout the rest of this talk. But this is kind of like a screenshot of some of the last and final work that I did as an undergrad and how it continued on to my work. And so with that background, I want to jump into the research, of course, while we're all here, and I've been eager to learn about sedimentation. If not, I'll try to make it as entertaining as possible. But I want to go into some motivation for why we study the glaciers and ice sheets, or even why I study the glaciers and ice sheets, and our current understanding of sedimentation within those systems. Then some methods and preliminary results within the work of this sediment model, and some of my future work within combining a sense of seasonality modeling and how that influences sedimentation as well. So if you have any questions throughout this talk, please stop me. And yeah, I'm excited. So I want to start off with this image. This is a plot by the INBI team, which is an observational group. And the important thing to show here, and they take observations of what sea level rise currently looks like right now, and they compare it against the IPCC reports with 5 different climate emission scenarios. So you might be familiar with this plot. If not, the red bar, or like the uppermost one, is where we don't kind of mitigate carbon emissions, and then the blue one is like we do take an active effort to like divest from fossil fuels, and the orange is somewhere in the middle. And so this black line is what we currently observe, and it's on track with the highest emission scenario. And so this is a rapidly increasing issue, and it's accelerating at a pace that we haven't seen before. And so what can we do to kind of explore why these observations are on track with this? I also want to show that there's an increasing effort to understand this changing ice sheet. And so there's a lot of lines on this plot, but I'll walk you through it. And so the orange one is global mean sea level rise since 1993. This is all relative to the Greenland ice sheet, by the way. I can't talk too much about Antarctica. There are other experts in the room that you can for that, but I'm mostly focused on Greenland. And then the cumulative melt velocity for Greenland. And the black line is Greenland losing mass relative to 2002. And what I want to point out here are these graded gray shaded bars, which are the amount of publications per year focused on studying the Greenland ice sheet. So there's a large collective on understanding this rapid acceleration and need to understand why is Greenland changing so quickly. And so there's a lot of processes that go into understanding the ice sheet. And I know this is a very complex diagram, but I want to point out that a lot of my work so far focuses on the subglacial part of this system. Gonna pop up. Cool. And so there are other experts that look at the surface of the ice sheet. Some of my seasonality work might touch in that, but most of my background the last few years has focused on this area where the bed lifts up and you have all this bed topography exposed. And so we're wondering what's the uncertainty associated with that area and what other interactions are associated with it. And so we can look to try to understand what our bed topography looks like. This map is a data product called Bed Machine, which is currently the state-of-the-art observations that also uses a data assimilation approach. And so these red areas are places of uncertainty within those observations where we simply just couldn't get it. Anything, and that's mostly due to the difficulty and expense of getting like every single radargram across like the central part of like the ice sheet. And so what Bed Machine does is they use this mass conservation technique to kind of see if we can, I guess, estimate other parts where we don't have like any bed topography observations and see what that looks like. And so that's why you see a lot of the middle areas having this high uncertainty where they couldn't gain observations. So this is how we currently try to understand subglacial bed topography and our efforts within that, and where we're missing some key details. In addition, the subglacial bed topography varies at all scales, and I like to use this image and animation. I hear that I say GIF and it's kind of problematic, but you know what, to each their own. We can discuss this after. So this animation on the right, and I know it's overwhelming, so look away when you need to. But this displays the concept that bed topography has this fractal behavior, or it has kind of like this self-similar repeating kind of dimension. And so it's hard to capture this within modeling because it varies at all like horizontal scales and spatial scales. And so we know that this is an issue when collecting observations and also when we try to model it. And so how do we see this in observations? This is a radargram from Jordan and others in 2017. And within a radargram, you just attach a radar at the bottom of the airplane and it flies over the ice sheet. And in this image, you can see where the air is, the ice layer, and ultimately the bed topography. And from left to right, you see kind of like a high fractal dimension behavior to like a low fractal dimension behavior. But the challenge with this is that the spatial or horizontal scale varies within all of these. So we can't use the same fractal dimension behavior for a single area or when you're looking at a larger area. So another issue within observations and modeling in terms of understanding the subglacial processes within glaciers. And so I want to shift more of the background and motivation to sedimentation and what my efforts are in currently in modeling that and understanding where observations are right now. And so in the 90s, quote me if I'm wrong, but there was this paradigm shift in recognizing that the bed topography under glaciers aren't all exactly hard bedrock. In fact, it can be soft and deformable when there's the presence of this water. And so this graphic on the right kind of shows that in terms of like you have this like hard bedrock system, and then that can change into kind of like this sediment water filled system as well. And so there's this idea and seen in some observations that the subglacial water, the presence of this water, can move the sediment around and deform the bed topography. And I want to play another animation. This is a numerical model representation of Taku Glacier in Alaska by Gringerhoff and others. And this is the model that I will continue to refer within this presentation. But this shows what we observe within observations, that glaciers can move around sediment and create these shoals or moraines. And so in the upper panel, you can see the glacier advance and retreat and kind of move sediment, which is this red line. And over time, the black line will kind of flatten out where it has this effect of smoothing the bed topography. And so we see that moraines build up over time. This bed topography changes over time too. And so this is is this really dynamic system of advance and retreat, which is seen in the lower panel of the grounding line, or where the edge of the glacier that's in contact with the bed moves back and forth throughout this profile. And so this is really cool and important because it shows that sedimentation is really important because it changes the size of these moraines and creates like a period of stability for these glaciers, but it also changes the shape of this bed topography. I want you to play again. And so a main finding from this paper from Brinkerhoff and others is that the presence of sedimentation does drive this tidewater glacier cycle, and under different climates. So this is the top panel where they have like a cold climate perturbed or like an intermediate. You can still see these different amplitudes of the tidewater glacier cycle, but maybe on different periods depending on the climate. And you can see that within the ice dynamics in the bottom panel, where you have like a higher rate of calving during some parts of the simulation, in addition to accumulation and ablation. And so just really want to drive home the fact that sedimentation is really important for controlling and understanding a lot of these dynamics in glacier systems. So what about outside of Alaska? You know, I talked about I'm focusing on Greenland, and I've only shown things within Alaska. And so there's recent work, well, actually it's 2011, but I hear they're coming out with another paper soon. So fingers crossed on that. I'd be very interested. But rates of sedimentation in Svalbard comes from this paper with Curl and others, where they did difference mapping between bathymetry swaths within about a 4-year time period. And within this plot, the glacier front is right here on the right. It's kind of like white looking ice. And they're trying to show areas of where there was sediment loss and gain, sediment loss being white, gain being black, and the size of these circles is the amount of sediment changed within these 2-time swaths. And so this also goes to show the importance of, even in a colder climate, there is the presence of the sedimentation factor, and it occurs at different amounts of accumulation too, as much as being 3 meters of sediment accumulation per year. And we also see this in AUV data, and others here at UTIG are interested in this, of course. But this is a bathymetry survey between 2004 and 2014 from Gulick and others, where they looked at the front of Hubbard Glacier and saw there was about 80 meters of like this moraine or sediment growth within this time frame. So that's like at a rate much higher than uplift. And for those tectonic people in the room, I would love to hear your input on this. And if you see this in other systems as well. And so it's really important to capture this amount of sedimentation, which is largely ignored in most large ice sheet scale models. And so a lot of my work is trying to focus on what happens when we start in a really simplistic model and kind of build up and understand how are these sediment moraines being built and what other dynamics are being affected by this process. And so bringing it back to this image and understanding what's happening within the subglacial parts of Greenland, it's important to understand the fundamentals of this mechanism before putting in a large ice sheet model. And so this brings me to my main research questions, the first one being really broad, and hopefully I can do some work to kind of attempt to answer that within my years here at UT. But do future projections for ice sheets change if we include this coupling between the ice and sediment? And what I can for sure accomplish, hopefully within this next year or 2 years, is what are the dynamics of a coupled ice sediment model in a Greenland fjord setting or an idealized Greenland fjord setting. And so I'm going to jump into some of my methods in terms of what is this modeling effort that I'm doing with the Brinkerhoff model. So we can simulate glaciers and ice sheets as well through systems of equations. And so within the schematic, I'm kind of going to try to paint a picture of how we represent these within a model. And so here you have your glacier and it's flowing from left to right. This red area is the sediment, and this purple area is the ocean. And so we can have this ocean interaction with the ice in terms of like the melting and calving that you might be familiar with glacier processes. We have this initial bed topography, and within my model, I vary that from about 1,000 meters above sea level to about negative 2,500 below to kind of represent a large Greenland setting in elevation and over a 600-kilometer domain. So idealized to an outlet glacier. And here we have systems or equations of mass conservation, and the sedimentation processes being included within this model are glacial, fluvial, and diffusion. later I'll talk about efforts that are being made to include other processes, but these are the main ones influencing the sedimentation dynamics within this model. And then we have the surface mass balance, which we adapt to a Greenland setting as well. And so through these systems of equations, we can simulate glacier change and see what happens to the system. And so I want to show what that system looks like. And so this is like an initial flat bed topography. And when we run this model for about 20,000 years, we kind of have this kink or this like depression formed in the bed topography and this moraine formed, which can see a long profile here. And so within these profiles, we can look for ice volume change, how much sediment is being produced, and how much ice, how fast the ice is flowing too. So ice velocity. Here I'm showing an animation or GIF of this 20,000 year simulation. And in the top panel, we can track the glacier profile over time and the ice volume changes that happen with it. We can track the grounding line position or where the end of the glacier and the bed topography meet. We can track the speed of the glacier. So how fast is the ice moving within these periods of advance and retreat, and the sediment accumulation over time. And so what I'm going to show you next, I believe, are the differences between two simulations of having sediment on versus off. So whether we have this sediment coupling turned on and we can have like erosion and diffusivity versus having no sediment at all and having a hard bedrock case. And so I have two preliminary results, and we're actively working on exploring this system within other means of statistics. So a big takeaway from some of our preliminary work is that, yes, including sediment within an ice sediment model, sorry, that made no sense. Including sediment coupled in this model does lead to tidewater glacier cycles in Greenland. To what amplitude? It's variable throughout time. And what I mean by that is kind of like this is ice volume in the top panel and then sediment volume, which makes sense because we have one with none. So it should be like that. And then a whole bunch of sediment accumulating over time. And then the ice velocity or how fast the ice is moving in the bottom one. And so we can see these tidewater glacier cycles in almost all of these plots, but the unique thing in this one is that in this cycle, it doesn't really reach baseline or where we have this sediment off case. And that's also followed within the second tidewater glacier cycle after that. And so we're really curious about how often does this happen and what's the amplitude and cyclicity of it. And so if we apply a Fourier transform series and kind of zoom in on the area or the fraction of that ice volume from the previous slide, what I really want to point out is these two peaks around 2000 and maybe like 3000 years is that gets at these kind of like half cycles in a way or smaller amplitude and that periodicity. This longer term signal is something that we're still trying to explore, which can be achieved through running this model for a much longer time and seeing what the long-term trend is. But what we can see within this one is around 2000 to 3000 years, we see these tidewater glacier cycles. And so current work right now is exploring this parameter space of what happens when we have different initial bed topographies, different angles, whether it's kind of like steeper or flatter, the different kinds of surface mass balance, and what other parameter space we can explore within this. And so far I've only showed you one type of setting for surface mass balance and one kind of initial bed topography. And so eventually we'd like to build up this complexity, working on different kinds of bed topography and introducing other sedimentation parameters or sedimentation equations and processes as well. So as I said before, these are the two main processes that we're including within our sedimentation equations, and hopefully we can build up in complexity for thermomechanical and mechanical deformation. We know that these systems could be at play. To what extent, we don't know yet, but what we can constrain right now within this model that was previously used for Alaska and now kind of theoretically using it for Greenland is glacial fluvial and diffusion. And so we can look to other fields in terms of what other morphology and characteristics within slope and aspect ratio can help us understand the rate of sedimentation. And here are 2 points for what Hubbard Glacier looks like in terms of their slope and moraines. And so some of you might be very familiar with this literature, maybe not. So I'd be more than happy to kind of sit down and walk through where we see influences of sedimentation and other earth systems and how that can inform our systems as well. And so a lot of future work is to collect these other observations. I know this is a lot up here, but what I want to point out is that here are these variables that we can constrain, that we should be able to constrain within our model. We just don't have the observations right now. And so a lot of our work in terms of understanding these tidewater glacier cycles is to go into the field and constrain more of these equations to have a more accurate model. So yeah, just emphasizing that there are so far no observational constraints, or not many observational constraints within a Greenland setting to constrain the sedimentation processes. And so this is in joint with other future field work with others here at UTIG as well, to go out to this area in central West Greenland. So this is an ice velocity map of Greenland, and this is like a zoomed in area. And what we'll do is go to these 3 glaciers and use an ROV to kind of do like this bathymetry mapping, take actual sediment grain samples from these sediment moraines, and hopefully use that to inform our models and also compare against what we're seeing within our simple experiments right now. And then we can build up this complexity. And the great thing about these 3 different glaciers is that they're all differing. They're all different in terms of like their recent retreat within the satellite era. So this one here at the bottom hasn't really retreated at all, and it's grounded. We have like this ice floating tongue and kind of like this ice age moraine right here as well. And here we do see some retreat in this upper glacier. And so this can be kind of used as a proxy to study other glaciers around Greenland where we do see sedimentation. And so hopefully this can influence and encourage other work to explore these systems as well. And so that was a lot of sedimentation. And I did mention that I also do some complex modeling with seasonality. So right before I started here at UT, I did an internship, remote internship at NASA Goddard with Dennis Felixson, an alum here. And together we explored the effect of using seasonal forcings within the ice sheet system model, or ISSM. And I'll go through some of that work, which is still also ongoing as well. And so a quick background into what I mean by seasonality. Within the literature, we define seasonality as observed terminus position changes, as during the winter time you have glacier advance, and during summertime you have retreat. And that's also depicted here on this plot on the right. The difference between the upper and lower plot is the type of calving style within these glaciers. But I want to point out is that during a 3-year period, we see that there are seasonal changes in terms of terminus retreat in the summer and advance in the winter, increase in melange and runoff during parts of the years. And so we know that there's this seasonal effect going on within glaciers. However, the issue or challenge that I was looking at through this is that all models, or mostly all models, just use an annual average. The IPCC reports also use annual averages. And so we see that there's this detail in seasonality, and effectively they all ignore it. And so we're trying to quantify what's the difference between using the annual and seasonal averages. And so our goal here is getting models to produce seasonality. The model or tool that we're using is ISSM. And we want to reproduce the observational record within the satellite era of seasonal forcings. And this just largely motivates the question of, does including seasonality bias our initialization or hindcast period within models and our future projections? And so I'm going to show you 2 experiments using ISSM, one with seasonal forcings and one with annual forcings. This is our research area that we look at. So this is a little bit south from the previous research area that I showed you. And the different colors show observed glacier terminus positions from 1985 to 2015. So with some glaciers, there was relative retreat, and with others not. And similar to the other glaciers, they are all differing in terms of like characteristics within their geometry, bed topography, catchment sizes. So a great proxy area to address other areas of the ice sheet as well. And so what does seasonality look like in terms of ocean thermal forcing and surface runoff? Here we have ocean temperature in, dang, I'm forgetting the data source, and I've been working on this for a while. But anyway, you can see in the blue, there's a lot more detail, and that's like the monthly record, and we take the annual average of this. And then we have surface runoff on the right. Oh, Ian for observations in RACMA. That's what I meant. Yes. And then then we have surface runoff on the right. And so we see that within the yearly one, it's missing a lot of the detail and changes that we observe within our observational record. And so this is only for one glacier. They're different in terms of the magnitude within others, but I just wanted to show this as a visual example. And so the big takeaway from this work is that when we apply monthly versus yearly climate forcing, there's this bias or offset between the two. The difference between the left and right plot is the amount of calving happening. So in the left plot, this is more calving within our model, and the right is less prescribed calving. Sorry, brain fog. But anyway, the difference between these two is that the red is in the yearly observations that we show with less detail, and the right one is the monthly one. And so we see that there's essentially more ice volume loss with the yearly and less with the monthly. And so we're trying to play with all these parameters to see how different rates of ice volume change over time and other efforts. And when we compare terminus positions, when we compare our modeled ice sheet extent, so that's kind of like this long wraparound one with actual terminus positions, we see that our model results don't capture all of what we see in observations. And to the extent of how much is the yearly versus monthly showing, we can kind of see if you, I really wish I blew this up more, but the red one kind of, which is the yearly one, retreats a little bit more than the monthly one. And with some of them, they don't exactly reach the exact retreat of where we see observations right now. And so we're working with different variables like calving, like we saw in the previous slide, and other sliding laws too, to see like what set of tunable parameters that we have best match observations. And so those are ongoing efforts right now. And so some key takeaways from both my sediment and seasonality efforts is that including sediment does lead to tidewater glacier cycles within ice sediment coupling and modeling, and the amplitude and periodicity with those vary throughout our simulations, and applying a monthly versus yearly climate forcing does create this bias and offset in terms of ice mass loss. And so, I'd like to start our conversation and start with these two questions in terms of what aspects of sedimentation modeling do you think we should further explore within our models, and what other systems where sediment is present and active can help inform our models as well. And so some quick acknowledgements. I'm funded by the Blue Sky Fellowship, so shout out to them, and also the CAC Foundation, which is funding a larger effort within our model exploration and sedimentation, and of course my co-advisors and those contributors. So I'll leave this slide up and we'll take any questions.
Yeah, I thought in your model, how are you making sediment?
How are we making sediment?
Yeah, in the model.
So there's this like very, very thin layer between like the bottom of the ice and the bed topography, where it is kind of like permeable, and that can move around, and also any water that's present on the surface does route to the bed. And so during like the spin up, so in the model we see that we start from like a zero ice, like ice-free state, and it builds up. And once it reaches kind of like this steady state, that's when like the cycles begin in terms of like all the sediments being pushed out in front of the glacier, and then the tidewater glacier cycle kicks in.
But the sediment that you're producing that you're turning on, is it an erosion process, or is it just coming in from the front of the foxhole?
Yeah, so there's like erosion and the glacial fluvial being output in the front, and then that diffusivity over time in front of the glacier as well. But it's mostly the processes that are happening right at the glacier front.
Okay. And is there much is underneath the glacier, is there much change in topography?
Yeah, so over time, the topography closest to the front of the glacier is what's changing over time. So we saw that kink in one of the animations, but further inland, nothing propagates. That's just due to kind of like where we set, I guess, like the surface mass balance as well to be changing. But we also haven't run this model for longer time periods than like 30,000 years to see how long that propagates inward. Yeah.
Yeah, I guess I have a question that's kind of follow up to Duncan's. Like you mentioned, our understanding about this would be started from hard rock. And then we realize we may have soft rocks or deformable at certain places. I guess my question is, we know how widespread the presence of sediment in your case is in reality.
Yeah, so I mean, what we see like within like swath bathymetry right in front of glaciers, it's like we can see like some output and like alluvial fans within some part of the system. But like actually getting samples of like what's hard versus soft, no. I haven't exactly looked at like seismic surveying like around Greenland as well, and I'm trying to study like more of like geology maps of Greenland too. But to an extent, yes, but mostly no. Yeah.
No, that's good, but it's a good question because how representative your initial model, it seems to me like you jump step by, I would first do it, I don't understand anything about geology, but first thing I would do is just to see what's the changes, just by simply put it in bedrock. If there is affected glacier before introducing the sediment, I would say, or that's already, you mentioned in the 90s, it was the assumption, so you already have good constraints on that.
I mean, I think the assumption right now, and this applies to like almost all ice sheet models except for one that I can know off the top of my head, they all use like the same bedrock essentially that have throughout time, and so that doesn't change at all. And so whatever is being produced by most glacier models and ice sheet models right now is, you can assume, hard bedrock. And so the amount of sedimentation extent, we can be very confident within Alaskan glacier systems. That's where the model kind of takes like most of the observations from, is Taku Glacier. But they also use like some estimations, to be fair. But yeah, sedimentation right now is really just like a guess and estimation and trying to define we're confident within these bounds.
So you said it's making the glacier more stable. Is that accounting like the thermal fluxes or anything like that between bedrock and sediment?
I don't think I understand your question. Can you repeat it?
You said that it's important sediment because it makes the glacier more stable, like less retreat or.
Yeah, so I guess what I mean by periods of stability is that the presence of sediment and these moraines over time is what the glacier stabilizes on, kind of like the pinning point. And then once it retreats off, then that cycle occurs again in terms of like retreat and then advance again to that current like moraine. So that's like, yeah, the important part of the sedimentation.
You said you mentioned you're looking at some geological maps and geology of the area. So with the bedrock, if it's just assumed to be a hard rock type, does the type of actual hard rock have an impact on any of the
Yeah, I would assume like there's different like erodibility between different bedrocks as well. The exact number, I don't know.
Can you factor that in at all? Like what's known about what's actually above on land?
Yeah, so there's like an initial erosion factor. I haven't changed much about it, but it is in like one of my future like ensemble runs to like change that erodibility.
Another question I had is, so you show that you're going to work on 3 specific glaciers for your sediment model. Why those 3?
One, they're funded. 2, I mean, Ginny and other advisors and people on this project have the most experience within that area. And so we can use like other observations and what we know within the satellite area in terms of how these glaciers behave. And yeah, we're funded.
No, because like more than likely your work is going to show it's important to consider sediment and security in our either glacier model or continual ice sheet model. And I was just wondering whether it's possible to apply your work to other places.
I mean, yeah, I think it's like my big pipe dream is to kind of do like bathymetry differencing between whatever bathymetry data is available within like all these outlet glacier systems, because I'm sure we can see in places where we do have differencing in that is it due to sedimentation, and quantifying how much and why. I mean, we've seen it like within Alaska, and I know some of our colleagues here have done it. Yeah, those like difference map within bathymetry. And so I can see where this work would transform and apply, and quantifying how much sediment is being produced by these systems. For the Antarctica case, I'm not sure. All I know is like subglacial drilling sediments and subglacial lakes that are happening, which I think is still super interesting, and seeing where that's being routed. But yeah, I think primarily in the Greenland setting, just looking at other existing bathymetry data and doing differencing between the two.
Are those data available, the imagery data? Like the differencing is just looking at the differences over time periods.
Sure, I think the detail that I would look for is like right up to the fjords. Kind of hard to do that in general, and so what's leading the way right now is like this ROV. I wonder if I included the last image. Yeah, so I borrowed this image from Junie, but this is like the ROV that we'll be using within our future field work. And I know that other glaciologists in the field, like European glaciologists, are starting to use like ROVs and AUVs to kind of map like right near the terminus. It's just that I feel like right now our bathymetry right at the terminus isn't as great, and it's more like assumptions and data assimilation.
And you said those rates were 8 meters per year?
Yeah, so that was at Hubbard Glacier in Alaska. Yeah, pretty high rate in that sense, but I know the Alaskan glacier, those are like very more temperate ones, which move a lot more and may produce sediment a lot more. And so we're not sure exactly for a colder context like Greenland.
Do you know if that was like how many years that was sustained over? Or like how many years those data were averaged over?
I think it was 10 years. Yeah. So 2004 is the bottom one, and 2014 was the repeat survey. I wish Sean was here. If you're in the recording or somewhere else, Ethan has a very important question. Yeah, 10 years.
So you had a slide with a lot of parameters that you test, so for sort of perturbation analysis. But I assume some of them you don't have actual perturbation constraints, so do like a Bayesian certainty analysis for that, or
The ablation uncertainty, I'm sorry, I couldn't hear you.
yeah, because you're gonna perturbate those parameters. Probably some of them you don't have the actual observational constraints. Or you
Definitely like surface mass balance, we can inform this, and hopefully after these like initial like bed topography test, we can incorporate some flow line topography that we have to kind of constrain or introduce like more observations. But yeah, I'm trying to start with like an idealized simplistic case and understand like what's the boundaries that we can test within this adapted Greenland setting. And when we start to introduce observations, like how fast does this system change, and track exactly what's controlling what too. But yeah, majority of this idealized work is kind of guessing and ballparking numbers, since we don't have much observations. If you love to fund me further, I'd appreciate it.
I didn't know it's possible.
Is there information on like the mechanical properties of the sediments?
Like thermomechanical
Like,
glacier.
part of your, or just like the cohesion or the frictional properties? Incorporated those. Because that curve you showed was just like cohesion dependent, the grain size.
Mhm.
curve.
In this system, yes. Is it true to Greenland? No. Do I know Greenland? No. But they do influence the system as well. And hopefully when we incorporate other equations, we can increase that sophistication of these processes.
The behavior of the moorings with the interaction, it's really similar to the curves you're getting from longshore transport. And the physics there, it's well known, so it's worth looking at that process and see if we can derive something from that. How the sediments behave with water motion, so here it's not water glacier, but it's very similar curves.
Yeah, I think it'd be interesting to see like guess we have like these little ice age moraines like right in front of the glacier terminus, and how long does it take for those to fuse? Because we do kind of have like sediment shelves that we might see like in offshore bathymetry as well, and so it's like my big question would be like, how long do those diffuse, and is that any different from what we see like in deep ocean basins or like alluvial river systems? Yeah, I don't know if anyone's like, nah, Mikayla, don't think about that, or anyone online have any questions? Yeah, Mikayla, thanks, Mandala.
So, how, was there a state change between the Ice Age, Greenland, glaciers, and where they are now, or was it pretty much the same processes going on?
Like, what processes are controlling
Right.
like the retreat?
Yeah, and then, was the ice sheet further out, was the system overrun in the past, and then.
Oh, yeah. Yeah, I think for most glaciers around Greenland, they've retreated since like the last ice age, but some like not as much, I believe. I'm not sure. Benjamin, if you want to put in your paleo input.
That's right.
GIFs or GIFs?
Gifts.
I guess I'll be saying animation from now on.
I like it when people call them movies.
Movies?
Yeah.
Silent films.
This cute little silent film. Well, I'm always around, well, that's not true this semester, but I'm usually around UTIG, if not main campus, for classes. So if you'd like to talk further about this work, or if you have any ideas, I'd really appreciate them. I didn't put up my email, but I'm CC'd in the email that was sent out for this. So don't be afraid to reach out, and thank you for coming. I appreciate it.
Yeah, well, next week.
That's so good.